So today's last talk is John Tsitsiklis, closed loop control of the network of processes.
Okay. Good afternoon. First, let me thank the organizers for inviting me. It's always a pleasure to visit Berkeley. So since this planning workshop, I thought that the idea was to not to talk so much about the last greatest results, but somehow to give a kind of bigger level perspective. On the other hand, I don't think I could eat the whole slot just being philosophical. So I'll try to do a convex combination of the two. That is, try to be philosophical, but kind of anchor the discussion on the basis of some more concrete work. And the concrete work I'm going to be using, the occasion is some work we've done with a student who just graduated, Kimon Drakopoulos, that we co-supervised with Asu Ozdaglar. So it's a workshop about real time. Let's see, how does that go away? Oops, no. Okay. All right, so I guess the first question is, what exactly is real time? If we take Steve Boyd's perspective from yesterday, basically if you solve an optimization problem every millisecond, that qualifies as real time. But if that's the case, I guess my talk will not fit the bill. Rather, I'll take a broader perspective that, in my opinion, what we mean by real time is basically that it's closed loop. And closed loop means that the world out there evolves, there is uncertainty, we don't know how it evolves, we get measurements, and then on the basis of the measurements we make decisions and we act and all that. And the time scale at which this happens could be Steve's 1 millisecond kind of image. But if you're thinking about controlling the Zika virus epidemic, obviously the time scale of where do you deploy what resources and all that, they don't run in milliseconds, they run in days or weeks. So the time scale, I guess, can range. Now, stuff happens in real time. On the other hand, even in real-time control, one needs to keep in mind that there can be a lot of offline computation to do well in real time. For example, your controller could be described by some nonlinear function that takes measurements and produces controls. But that nonlinear function, you can train it, you can design it by doing huge amounts of offline computations. For example, it could even involve training some kind of deep neural network to learn the right map and use that one. And also the type of questions that I think are even more interesting are even at a higher level, which is how to architect the whole thing. That is, okay, you can spend a lot of effort to solve a particular optimization problem, but you can also ask the question, why solve this problem and not think about a different configuration of how to set things up and solve a different problem. All right, now, so that's one part, what's real time. My title talks about networks. So what I meant by networks was this kind of subfield that sometimes people refer to as network science. And let me just do a quick history of this topic to see where I want to kind of give a big framework to place what I will be talking about. So network science, I guess, starts with the classical work 60 years ago or so. We get models of random graphs or random networks, either drawn probabilistically in one shot, or later there were models of preferential attachment where things come and go and the graphs grow. And so in this phase we get just models of graphs. Then the next stage is to start having interesting things happen on those graphs. So at each node there's some kind of state variable, and these state variables evolve through an interaction. And there's a number of standard models, or the clean models in this literature, the types of models that one would put into a textbook. So these are models of epidemic propagation or cascades or contagion, whichever you want to call them. There's models like the voter model where opinions evolve. You look at a random neighbor and you adopt their opinion with some probability, or different models of opinion dynamics where you look at your neighbor's opinions and you take the average of those opinions to form your own. And then a bunch of other local type interaction models like from Ising type models or generalizations of that. You can think of dynamic Bayes nets or Markov random fields that evolve in time. All of these kind of have the same flavor in that they're local interactions that involve probabilities. So you get from here a menu of processes, and that allows for a huge literature to be built on each one of these categories. The references probably run in the thousands, and there's lots of stuff that one can do. All right, so huge amount of literature on analyzing those processes. Then the next thing that one thinks about is, let's do something about those processes. How can we affect them? And literature started coming up, for example, thinking about the epidemic context. Natural question is, okay, if I don't want my epidemic to spread, what can I do? I might go and vaccinate a fraction of the nodes. What kind of fraction do I need to vaccinate so that it will make a difference? You find the answer. Then you ask, well, can I choose intelligently who to vaccinate? Maybe only vaccinate those nodes that have high degree, or those nodes that are kind of central in the neighborhood, in the network. And that gives rise to a fair amount of literature. Another type of intervention of this kind, which I would still call it a static one, is consider some opinion dynamics model, where everybody looks at their neighbors and gets affected. Suppose I could pick 10 of the people in the network and tell them, you don't listen to others, but you always say Coke. I'm going to drink Coke. Okay, you're a stubborn agent who's not going to change your mind, and this way you're going to have an effect on the others. Who should you bribe to keep shouting Coke and all that? So there's literature and papers are coming out in that direction the last few years. And where I want to get to is that these interventions are kind of static. That is, the network will run, the process will run, we do something in the beginning, and we let it run. The next phase, where I'm trying to get to, is to go into a closed loop control, where you actually do something while taking into account the state of the network. And so here, then, one starts thinking, what are the kinds of formulations that one should consider? What kinds of hammers should we be using? What are the bottlenecks? How much progress can we expect to make? So I'm going to illustrate a little bit of that by talking about a specific piece of work, and then go back to the more philosophical kind. So the specific work involves the epidemic model, so-called SIS model. We have a graph. The nodes at any time can be infected, which is red, or non-infected, or healthy, which is white. And the set of infected nodes evolves in time according to the dynamics. That is, if a node is infected, it becomes healthy at a constant rate. What does that mean? It means that in every delta time unit, there's probability rho times delta that I'm going to switch to being healthy. On the other hand, infections happen, and the rate at which a healthy node becomes infected is proportional to the number of infected neighbors. So this node gets infected at rate 2, which means that in delta time units, there's roughly 2 delta probability that this node will turn and become red. So this is the standard SIS model. It's a continuous time Markov chain, and the state of this Markov chain is the set of nodes that are infected at any given time. All right, the total amount, if you think of this rate, rho, that's the rate at which nodes get cured. Think of this as the amount of curing resources. We have a rho resource that's at each node, like our capacity or our power to fight the disease at any node. In some sense, you're using curing resources equal to rho times n. Now, at any time, what's really happening? No, if you have so many infected nodes, each one gets cured at a rate of rho in a probabilistic sense. So in a probabilistic sense, there's a drift that nodes get cured roughly at this rate. But at the same time, nodes will also get infected. And the rate at which infections happen is the cut that separates red from white nodes. Each one of the arcs that crosses this cut is a path along which an infection can be transmitted to a healthy node. So the number of expected number of infections per unit time is proportional to this cut. And these two fight each other. The curing rate drives down the number of infected nodes. The infection rate drives it up. Where does this model come from? There's all sorts of narratives that give inspiration for models of this kind. For anything that can propagate and that you like or you don't like, you might think that perhaps it's modeled by a model of this. The literature on this topic has looked basically into static strategies. If we have a total budget of a curing rate, at which nodes should we put it? But that would happen in the beginning of time. Various ways of studying this question. Most of the work actually has been on with approximate kinds of analysis, things like mean field approximations, heuristics of various kinds. Rather little literature that looks into dynamic strategies that tries to allocate curing resource in real time. Some of it was, again, approximate with mean field models. And there was one paper that we knew that did actually rigorous analysis, but for a very limited set of graphs where the answer was not that hard to see what it would be. So that's where we're taking off from. So let's think again about the static model. Instead of having a constant curing rate at each node, a rate that's the same for each one of the nodes, perhaps we can assign more of that rate at some nodes and less to others. Those that are more vulnerable perhaps should get a higher curing rate. But let's think of our curing budget. The total is how much curing rate we have sitting at each node at any given time. So to make that into a dynamic problem, in closed loop, would be one in which we have a same budget of a total curing rate, but we allocate that curing rate to nodes in a time-dependent fashion and depending on the current state of the network. The first obvious observation is, of course, that in that case you should only allocate curing rates at nodes that are infected. There's no reason to waste your resources elsewhere. So, of course, in that sense, this is much better than that, because in the static model, your curing rate may be sitting on a healthy node and it's not doing anything useful. So in this context, we would like to do something if an epidemic has started, to extinguish that epidemic and to have that happen quickly. And you can rephrase that question, you can turn it around and ask, what kind of budget do I need in order to kill the epidemic quickly? Okay, you could think of trying to solve that problem in an exact way. The exact methodology for dealing with such problems is, of course, dynamic programming or Markov decision theory. You can write down the objective of minimizing the expected time to extinction. Dynamic programming, in principle, gives you an optimal policy. But to run dynamic programming, you need one variable for each state. A state in this context is a configuration that is a subset of nodes, who is infected and who is not. That's an exponential state space. That by itself doesn't prove that the problem is intractable, but I think there's at least one person in this room who could prove that the problem is at least NP hard after thinking about it for 10 minutes or so. All right, so you cannot, that will not really take you anywhere if you try to go for an exact solution. One could think about approximate dynamic programming methods, which are pretty powerful and can give you good solutions if you're willing to spend the time to get them to work right. So in approximate dynamic programming, basically the value function of dynamic programming gets approximated by some parametric form, and quite often it gives good solutions. we might get solutions that are good enough, let's say, to be quote-unquote practical, if we're supposed to be solving a practical problem here. And now, work of this kind has been going on for some time, has had its ups and downs, hasn't been heard that much lately, but now with deep neural networks and deep reinforcement learning out there in the news, one is kind of tempted, okay, let's throw that hammer in there, yeah?
So are the best rho proportional to the degree, or is that?
It's not, no, it's not necessarily proportional to the degree. I don't think there's any theorem that gives a simple characterization. At best, probably David might know the answer better, but at best it would be some way, an efficient algorithm for optimizing the rho i's or getting them close to optimal, but there's no clean answer to that. All right, so we could throw deep neural networks and get, if you give me an instance of this problem, give me a graph, generate a solution. That would be an interesting exercise. I'm not sure if it's an exercise that's worth doing, because you solve the optimal problem for a specific graph, you have it there, okay. What do you do the next day that you're dealing with another graph? You retrain your deep neural network, and in the end, do you even get a decent publication out of that stuff? I mean, it's one thing to solve the problem of to get a deep neural network to play Go well, because that will get you in the New York Times, but I don't think that a good policy for that problem will attract that kind of publicity. So when we want to study those problems, sometimes it is that we actually want to compute solutions, but sometimes maybe we want to get insights that will help us. So let's take the other road instead of DP here and think about what insights we can get. So what's the structure of the problem? The structure of the problem is the following. We know that any epidemic is going to be extinct eventually. Just because of randomness, it may happen that all the infected nodes suddenly become healthy and it dies off, but this is a rare event. The expected time until it happens, in general, would be exponential in the number of nodes. But if we have enough Turing resources, if we can guarantee that at any time the total Turing rate that we apply to infected nodes is bigger than the cut, which is the rate at which infections happen, then we're going to have a downward drift in the number of infected nodes, and the time to extinction will be small. So we know that with enough Turing resources, we can get fast enough extinction. How many Turing resources do we need? Let's get some insight. Well, if we have a line graph, to get quick extinction, you could give a Turing rate of 2 at each one of all the nodes. Infections along that arc happen at a rate 1, but curings happen in that node at a rate 2. Curings happen faster, so we're okay, but we're using a curing rate which is constant at each node, so the total budget we're using is order of n. But it's not hard to think of a dynamic policy that does with very few curing resources, starts from the left and start curing nodes one at a time. So I put a curing rate of 2 here, so there's probability, twice as much probability that this will become cured as opposed to this one becoming infected, so that boundary keeps moving at a constant rate, and we get quick curing with a constant budget. And you need a constant budget. Now, how about a more complicated graph? If you have a mesh, if you have a configuration, if you were to do things statically, you could give, let's say, a curing rate of 5 to each node. Then at each node, curings would happen faster than infection, so that boundary would keep moving. That's a budget order of n, but we can do better. Think about putting all your curing resources just on the boundary, on the red nodes, and my curing rate is bigger than the rate at which infections happen locally, so that this would be pushing that boundary at a certain rate. Okay, but what if the configuration is not that nice and there are some holes, so that is also part of the boundary? Should I put curing resources here? Not really, that's a waste. Let that node be infected, don't worry about it. Think about sort of the real kind of nice smooth boundary and try to keep it smooth, perhaps by first curing that node, get a smooth boundary, and then try to push that boundary that way. And such a strategy basically keeps a boundary that has size roughly order square root n if we have n nodes, pushes it at a constant rate, and gets a curing that's kind of fast. And so square root n would be the amount of resources for fast extinction if you have a mesh graph. Yeah?
You could just use the simple strategy of vertical line, just like your other one, just move it across, right?
Yeah, okay, sure. I could just put all my resources here.
Well, just on a vertical line going from left to right and just go over it.
Yeah, it's essentially the same. Okay, so square root n is the amount of the budget that we need. Where does that number come from? Well, it's really the cut width of the graph that we have here. Just in case you don't know what cut widths are, suppose that you start with all nodes infected. Crusade would be to start curing the rates one at a time. And as you do that, while you do it, your nature is fighting you in proportion to the cut that you are facing. So kind of the cut is the rate at which nature is fighting you at any point if you were to deterministically try to cure one at a time. And the worst fight will be at some point in the middle of this process where you find where the cut is biggest. Okay, suppose I want to cure the nodes one at a time in a way that I do not have to face a very large cut along the way. So I minimize over all crusades the maximum cut that I'm going to encounter. And that quantity is called the cut width of the graph. And the basic claim is that this is the quantity that determines how hard it is to cure a crusade. So for the mesh, the cut width is of course square root n. In general, the cut width is NP hard to calculate. On the other hand, still as a concept, it's a well-defined concept. If for a graph we can approximate it, it's something that we can use. So the theorem would go if the budget is at least a constant fact, a little above the cut width, then there's a policy that achieves quick extinction. And the idea of that policy is to find that optimal deterministic crusade and have the stochastic system try to track it. Now, random stuff will happen. Things will not happen exactly according to plan, but you can use the little extra budget that you have to kill the deviations from the plan and then continue sticking to the plan. Okay, that policy is essentially optimal. And there's a kind of matching lower bound, at least for graphs that have, if you take a family of graphs in which the cut widths grow in proportion with the number of nodes, so and still their bounded degree, if the budget can still be linear, but by a smaller constant factor, and it's below the cut width, then any policy that you might consider will have an extinction time, expected extinction time, that grows exponentially with the size of the graph. And the idea of the proof is that when you start with everybody infected, your cut is 0. When you end with nobody infected, your cut is 0, because the cut width is whatever the cut width is. You have, at some point in the evolution, you will have to encounter such a big cut. And when you encounter it, the rate of infections is bigger than the budget that you have. So it's an uphill fight, fighting a drift that's against you. Crossing that barrier has exponentially small probabilities. That's kind of the rough idea, although the execution of this argument is infinitely more complicated. Just encountering a negative drift in one place is not enough to say that it's a big barrier. One needs to argue that this barrier lasts for a fair amount of time, so it's a big battle that we are going to be losing. Okay, so this is just an example of taking standard textbook problem from network science and posing a closed-loop control version of it and trying to make as much progress as one could. For that specific problem, there's a fair number of open questions that are left for variations of it. But let me talk about what one could do next by sort of taking this as an exemplar paradigm. Okay, just repeat. Look at your textbook, find all the list of models out there, and try to do something of that same kind. So in each one of these models, one can pose problems of this type. Now, of course, all of these involve exponentially large state spaces. They're intractable, so in each case, one needs to hunt for the right formulation where you can prove something that's both non-trivial and still possible and mildly interesting. So that would be the control theorist's agenda. Then, chapter 2 in systems and control education, at least in my days, would be that one then looks into inference. So for all these models, you can say now, suppose that we have partial observations of the state. I mean, so far in my formulation, I had assumed that some controller looks and sees who is infected and who is not and does something. Okay, so inference problems. Good literature out there, but plenty of room if you consider all possible variations to ask other questions. So that's a popular topic in inference. You observe the trace and you try to figure out who was the node that started the epidemic. Okay, who was the first person that had the Zika virus, let's say. Or if we monitor it while it's evolving, the standard filtering problem is to try to guess the states of those nodes that you do not see. If you want to up the ante, you also active probing. So a flu epidemic may be happening in some place you don't know, or maybe a more serious epidemic. Should you go and test random people and how many and who and so on? That gives a class of problems that's quite non-trivial and interesting. Okay, and then chapter 3 in systems and control education is that you do both inference and control, which means controlling a partially observed system. So that takes us one exponential level up in sort of difficulty. So here one has to be very careful on how to choose formulations to get anything to be interesting, anything interesting to say. So that's pretty open-ended. But now let me switch hats. So far up to here, I've made no pretensions about doing anything useful or practical. Just mathematician sees, okay, earth was rainy, beautiful, I know control. Let's see what I can prove, have plenty of fun with it. It's just a mathematician's exercise, recreational or professional, and that's fine. Now, if we want to transport ourselves to other worlds. One possible world is to do what's happening in the, let's say, the narrative sciences. Take those models, build narratives about them, do some illustrations around them with math formulas and make a story, and sort of sell whatever you want to sell in the first place. So that's one direction of work. But if you want now to wear the engineer's hat, you want to do something useful and realistic. Those sort of concrete questions. For example, instead of modeling epidemics by looking one node at a time, probably you should be looking one village at a time and talking about the fraction of people who are infected in that village, as opposed to keeping track of my aunt and my grandmother separately. Yeah, that's kind of nitty-gritty. But at a higher level, models should have some relation with reality. So first thing we should be, before we play with the model, it should fit with real-world data. And there's not a huge amount of attempts as a percentage of the literature in this field, how much tries to do that. Okay, so we should fit models to data. Now, Steve Boyd told me yesterday about a nice quote that I traced. Von Neumann said, give me 4 parameters and I can fit an elephant. Give me 5 parameters and I can also make it wiggle its trunk. And actually you can fit an elephant with 4 parameters. So just fitting models, the fact that your model fits the real world data doesn't mean anything. You may very well be overfitting and your model might have no predictive power, so you need to validate somehow, validating a specific model on the basis of data, and that's kind of serious and difficult business. It's much more frustrating and time-consuming than proving theorems, and for most people it's not as much fun, but it has to be done. Even the statistical methodology itself has to be validated. That is, if my methodology, I use it on some graph, and I think that I saw a power law, I should test my methodology on data generated from elsewhere that are not power laws, and see if my method always says I see a power law, I see a power law, probably the method is not good. And there's
You're
a
past
lot...
your time, by the way. You're past your time.
Ah, okay. Power law. It's the last line. And finally, even harder. Even the harder part is that even if we have a model that's statistically sound, fits the model properly, has been validated and all that, if we want to apply it in a control setting, it's not automatic at all that your model will still be applicable. So the model may be very well capturing the truth of what happens the way a system is operating now, but if you start operating it differently, maybe the dynamics will change, people will behave differently. So if you see that your neighbor is always shouting "Coke, Coke, Coke," maybe you just shoot your neighbor and get him out of the network. So the dynamics are not really what you have been assuming. So there's lots of very good and rich agenda here. One can see what can be done. There's lots of good work that has been happening in those directions, but I think it's really touching only a small fraction of what's possible.
So one thing I was thinking, I like your dynamic model. One thing I was thinking about though is it sometimes costs time or resource to move the current around. Did you kind of look at that?
No, we didn't.
Okay. That would be interesting.
Yeah. No, the model is really stylized and it's a toy model.
Yeah, yeah.
I don't know if you realize it, but an optimal policy is actually to shoot all your resource at one node at a time. There's no advantage in spreading your resources in multiple nodes, for example, so that's an unrealistic part,
Yeah.
and plenty of other things that one can criticize. That's why I'm saying it's more like having fun with math,
Yeah.
trying to get some insights, but without claiming.
Well, at least it's getting a little closer.
Yeah.
So my question is identical to Mike's, but I will rephrase it slightly so I can ask a little bit more. Has anyone else considered models that involve some friction to move your resources around dynamically, or are there other
In such network type problems, no. In problems, I think, where you have, let's say, sensors that are kind of hovering and they can do a job, but then there's a cost to go there and measure it there. Yeah, there's literature of that kind, but it's, I think, very different.
There's been lots of work in the public policy literature on immunization strategy, like Larry Wine at the Stanford GSB, I think, but that's not, it doesn't model the micro network structure. I thought that point you made was interesting, John, about kind of the value of modeling the network. Actually, that was the question I was going to ask is, right, I mean, there's a lot of fluid models that are used for immunization policy. And those fluid models, I guess, they have very complex sort of differential equation description of the macro dynamics of the system. They don't really model the network. It would be, that seems like a very natural kind of validation test of the value of network modeling. Like there, if you were to get down to the level of modeling network interactions, would it lead to substantially different conclusions about what the right policy is?
Well, for real world medical epidemics, I don't think that the micro level is right. I mean, the fluid equations would be proper, but then you would have to kind of choose your granularity, being neighborhoods or villages and all that. So my student actually tried to do this at the level of the 50 US states. So there's the 50 states and flu epidemics happening, and then there's people who travel, and there's data about interstate travel, and try to figure out how much interstate travel affects the infection. Turns out that doing the real work is infinitely more complicated than the practical one, because the flu epidemic model is nothing like this plain SIS model. There's a temperature and humidity is the main driver of the epidemic. And somehow you need to model that effect, learn it, take it out, and then see if there's an extra increment that comes from travel. So that last chapter of the student's thesis is yet inconclusive. We can see the questions there, but the data are not there, they're not so clean. The true model is much more complicated.
Any more questions? So thank you.